Section 4.1 Maxima and Minima. In general, there are highs and lows found in a function f with a certain interval. And in a nutshell, that's a max and min. When we have a graph, say like some type of polynomial type of function, there are high peaks, there are low peaks, and we can have a lot of highs with a really, really larger high one, and lots of lows with an ultimately even lower low. These are maximums and minimums. We'll learn in this section how to find them and a bit more about some theorems that help us develop these ideas. To begin our definition of maximum and minimum, let f be defined on a set D containing C. If f of C is greater or equal than f of x for every x in D, then f of C is an absolute maximum value of f on D. If f of C is less than or equal than f of x for every x in D, then f of C is an absolute minimum value of f on D. An absolute extreme value is either an absolute maximum or an absolute minimum. Here we have 4 pictures where we can kind of go along and see loopholes to these arguments of a maximum and minimum. In general, it needs to be a closed value. It needs to be a value in your function, something that's open, or like an open circle or point in your function that would make it not a maximum. So here we see this low peak and this high peak. The low peak would be a minimum, except it's not defined. It's an open interval. The high peak is closed, so it is a maximum. Similar graph, but with these high and low peaks both as an open interval. That would make them not maximums and not minimums. We have another picture where we see a low peak that's closed. That would be a minimum. A high peak that's open, that is not a maximum. We have an absolute minimum because it's because it's closed, but we do not have an absolute maximum because it is open. So be very careful for that. Theorem 4.1, Extreme Value Theorem. A function that is continuous on a closed interval AB has an absolute maximum value and absolute minimum value on that interval. So remember, it needs to be continuous, meaning a cheat way to remember a continuous function is that when you draw it, you never lift up your pencil. That's a way to consider something that's continuous. It also has to be closed, meaning there isn't any open parts to our function. Example 1. For the functions below, identify location of the absolute minimum value and the absolute maximum minimum value on the interval AB. Do these functions meet the conditions of the extreme value theorem? So we listed 2. It had to be continuous, that's 1, and it had to be closed, that was 2. From there, we can potentially find maximum and minimums. So our first one, we see that it is closed. We see those points are closed circles, so it's closed. We also see that it's continuous. There is no breaks along our function. And because of that, we can safely conclude that that low peak at C is a minimum. So we can say something like, thus by extreme value theorem, the minimum is at C. Now for the next function, we see that the next picture, it is not continuous. There is a break. And also, we have open intervals. However, we can still define an absolute maximum at this peak that's closed, C. It's the highest peak within our function. So, however, it still has an absolute maximum at C. Next, a couple of definitions in a theorem. Definition of a local maximum and minimum values. Suppose C is the interior point of some interval I on which f is defined. If f of C is greater or equal to x for all x in I, then f of C is a local maximum value of f. If f of C is less than or equal to f of x for all x in I, then f of C is the local minimum of the function. So meaning within your general or your function, it's just a lower value or it's just a higher value in your graph. Theorem 4.2, Local Extreme Value Theorem. If f has a local maximum or minimum value at C, then the derivative exists, and therefore f prime of C is equal to 0. That's so important because it's telling us that if it does have a maximum or minimum, then it could be found in the derivative when the derivative is 0. Next, we have definition of a critical point. An interior point C of the domain of f at which f prime of C equals 0, or f prime of C fails to exist, is called a critical point. Example 2. Find the critical points of f of x equals x over x squared plus 1. So according to our critical point definition, and also our local extreme value theorem written right above, a critical point would happen when our derivative is equal to 0. So let's go ahead and find that. So first, let's go ahead and find the derivative. Let's go ahead and solve our derivative by setting it equal to 0. And that's enough to find your critical points. If you want to move forward, you can also find your potential maximum minimums by evaluating at that value. So you can also evaluate and solve. Okay, so let's begin by finding our derivative, f prime of x. So we have quotient rule. So we have the derivative of the numerator, which is 1, times the denominator, minus our numerator times the derivative of your denominator, which is just 2x, divided by your denominator squared. So our derivative is x squared plus 1 minus 2x squared divided by x squared plus 1 squared. And we can clean it up. We can combine like terms in the numerator. 1x squared minus 2x squared gives us negative x squared. So I have 1 minus x squared all over x squared plus 1 squared. Alrighty, let's go ahead and solve. So let's set our derivative equal to 0. I have 1 minus x squared divided by x squared plus 1 squared equals 0. We multiply the denominator to both sides. It turns out to be 0, so we're just left with 1 minus x squared equals 0. We add x squared to both sides, so I have 1 equals x squared. We take the square root of both sides, so I have 1, or plus or minus square root of 1 equals x. So I'm left with x equals plus and minus 1. So these are our critical points. Now, if we want to find the maximum and minimum, we just need to evaluate at those points. So let's find f of 1 and f of negative 1. Now again, your function f is this one. Let's be careful to not confuse our function and our derivative, so be careful about that. Alright, let's go ahead and evaluate. So f of 1 is 1 over 1 squared plus 1, which gives us 1/2. For negative 1, I have negative 1 over negative 1 squared plus 1. We're left with negative 1 over 2. So we have these special values. We have a point at 1 and 1/2, and a point at negative 1 and negative 1/2. Now we look at the outcome. Now the one that's more positive would be higher, and this would relate to a maximum, and the outcome that's negative would be more lower on the graph, thus being a minimum. So that first point of 1 and 1/2 would be a maximum, and that point of -1 and -1/2 would be a minimum. Okay, let's go ahead and work out this next example, example 3. So for A, we want to go ahead and, well, let's read that important procedure. So this is your procedure for locating absolute extreme values on a closed interval. Assume the function f is continuous on the closed interval a, b. 1. You want to locate your critical points, c, in your interval ab, where f prime of c equals 0 or f prime of c doesn't exist. These points are candidates for absolute maximum minimum. So we're going to find our critical points. We find them by saying your derivative equal to 0. And these are your candidates for absolute maximum and minima. Not to say that they are. There's also funny points that can give an derivative of 0. Next, we want to evaluate at the critical points and at the endpoints. 3, you want to choose the largest and smallest value of your function in step 2 as your absolute maximum and minimum values. If it's continuous on an open interval, then the absolute extreme value occurs at all interior points. Let's do example 3. So let me split my page in half so I have enough room. So according to our rules above, we first have to find the derivative and set it equal to 0 once we find it. So for our function, f prime of x, luckily it's just power rules, not so bad. I have 4x cubed minus 6x squared. Now I need to set it equal to 0 and solve. Okay, we can factor out 2x squared, so we're left with 2x minus 3. We set each one equal to 0. Each factor, 2x squared equals 0. 2x minus 3 equals 0. We're left with x is equal to 0. X is equal to 3 over 2. And these are our critical points. These are points that could potentially lead to a maximum or minimum. We're not too sure. We need to figure them out. So we need to evaluate our function f, our x to the 4th power minus 2x cubed at those points. So I need to find f of 0. I need to find f of 3 over 2. But you also need to test out your interval according to your rules. That's step 2. So we also need to find f of -2 and f of 2. I need to plug those in and see what we get. So I have them worked out for you, so I'll just give you the result. F of 0 is 0. F of 3 over 2 is -27 over 16. F of -2 is 32. And f of 2 is 0. So amongst these values, which is higher, which is lower? So we have a minimum and a maximum at at 3 over 2 and -2. So we can say something along the lines that the largest of these function values is f of -2 equals 32, which is an absolute maximum. So we have an absolute maximum at f of -2 equals 32, or you can write it as a point, -2 comma 32. And it's a maximum along the interval given, which was -2, 2. We also have a local minimum, or an absolute minimum, at f of 3 over 2, which resulted in -27 over 16. And there we have it. Now let me give you a quick sketch of your graph so you can see what we're looking at. I didn't include it because I didn't want us to steal from our conclusion. So our graph looks something like this. Now let me label these values. So we have 0, -2, 2, and 1. So we see here would be our maximum that we found, and here would be our minimum that we found. Now, at these zeros are these values that result in a 0 in the derivative. However, by testing all the critical values in our endpoints, we were able to conclude and find a maximum and minimum to this function. Okay, let's do another one. Let's do part B. We have g of x equals x to the 2/3 power times 2 minus x on the interval of -1 and 2. Let's start off by finding the derivative. So g prime of x, we have to use product rule. The derivative of x to the 2/3 be 2/3x. Let's subtract 1 from 2/3 as we're supposed to, but let me show that work so that we don't make a silly mistake. So that would be -1/3 times the second, 2 minus x, minus my first product times the derivative of the second, which would be -1. Let's clean this up. Let's distribute let's distribute that in. So we're left with 2 times 2 is 4. 4/3x to -1/3 minus 2/3x to the, this is 1, so we would add those exponents. -1/3 plus 3/3 would give us 2/3. And then we have, oh, why did I write minus? Product rule is a plus. So we have minus x to the 2/3. All right, you can clean this up. These are actually like terms, so we can add them. So we're left with 4/3 x to -1/3. And we can factor out, we can add them. 3/3. So we have -2 plus 3, or -2 minus 3, which is -5/3x to the 2/3. Now you can leave it like this, or you can try to create a common denominator by factoring out that lowest common, or greatest common factor, lowest common factor. So we have x to the -1/3. So we're left with 4/3 minus 5/3x. Now, if you're confused when that happens, remember when you add them, we want to get 2/3. So you can also think of it as -1/3 plus x equals 2/3 if you want some more detailed reason for that. All right, so that we can rewrite this to be 3x to the 1/3, 4 minus 5x. That was a lot of work for the derivative. Okay, let's go ahead and set it equal to 0. If we set it equal to 0, we're just left with the numerator. So we are left with 0 is equal to 4 minus 5x. X is equal to 4/5. Okay, so now we're left to test these critical values. Now, in addition to that, we have another critical value to consider. Well, let me first list the ones we would have. We have the one we just found, so we need to find 4/5. We also need to include our interval, which is -1 and 2. But we also need to include values. So let me go back to our definition. Our definition for a critical point. an interior point C of the domain of f of which f prime of c equals 0, or f prime of c fails to exist, is called a critical point. So we have another critical point because our derivative fails to exist when our denominator is 0. So we also need to test f of 0. And that's why this example is nice, because it takes us to this other point we need to consider for a critical point. So let's evaluate these. We plug them into our original function f, or actually it's g. Let me tell you the answers so that we don't have a long video of just evaluating. So g of 4 over 5 is about 1.03. G of negative 1 is 3. G of 2 is 0. And g of 0 is 0. Now, I made the mistake of writing f, it's just a habit. Our function is actually g. Okay, now we're just left to look at our answers. And we want to see when our answers give us high values and low values. So we see that the largest of these values is at g of negative 1, which is 3, which is the absolute maximum. Now, the least of these values is 0, but it happens twice. Therefore, g has an absolute minimum value at the critical point x equals 0 and the endpoint of 2. So let me show you how this graph looks. This other one's called a local maximum. So our graph looks like this. So we see that we have this absolute maximum, which we derived, that happens at negative 1. We have this other local maximum. It happens, but it's not the largest maximum, and that's at 4 over 5. And then we have these two low peaks along our function. Let's do another example. A stone is launched vertically upward from a bridge 80 feet above the ground at a speed at 64 feet per second. Its height above ground t seconds after launch is given by f of t equals negative 16t squared plus 64t plus 80 for 0 to 5. When does the stone reach its maximum height? So let's draw a quick image, a silly image, just so we can see what's going on. So it's launched upward from a bridge, and it's going to go back down because of gravity, right? So we're trying to find its maximum height. Well, this would be found by finding the derivative and trying to find some critical point. Okay, let's go ahead by finding the derivative of our function. So we have this function f. Let's go ahead and apply the derivative. So I have f of t, or f prime of t, which would be negative 32t plus 64. Let's go ahead and set it equal to 0. All right, and solve. So we can factor out a 32, a negative 32, and we're left with t minus 2 equals 0. T minus 2 equals 0. We're left with t equals 2. So now we're left to evaluate at this critical point of f of 2 plus also our bounds, which is from 0 to 5, f of 0 and f of 5. So we plug them back into our original function. At 2, we get 144, At 0, we get 80, and at 5, we get 0. So which is the highest value, and thus resulting in our maximum? So on the interval from 0 to 5, the absolute maximum occurs at 2, at which the time of the stone reaches a height of 144 feet. Because the derivative f prime of t is the velocity of the stone, the maximum height occurs at the instantaneous velocity when it's 0. Alrighty, so that's pretty cool. So we can see how we can apply these max and minimums into a more real life situation. I have another example in case you'd like to try it, and I put a reference as to the book that we use, since I do use pictures. Alright, that's section 4.1, maximum and minima. Thanks.